Got to start it after the last one, so. Perfect.
Perfect. So, Spark packages, check it out. Fun little side story, search flux capacitor. You'll see this project, the project we're all working on here. I've given it 5 stars. I've actually logged in as somebody else gave it 5 stars, just so I could jack it up a little bit. Have to contact the Click Farms and see if they can help me out. I was in Helsinki. Finland? Yeah, Finland. The home of Santa Claus, I found out at the airport. They were very proud of that, because it's near the North Pole. Anyway, I'm doing a meetup, and the meetup organizer, I actually had a screenshot of this because I was explaining to people about Spark packages. And he actually said, dude, what's that pipeline thing, man? I saw it the other day. And it was like right at the beginning of the meetup. And I'm like, that's actually what we're going to be doing all day, like the next couple hours is this pipeline craziness. So yeah, he felt kind of bad. Yeah, I got a bottle of booze out of it, which is pretty cool. Some Finnish booze. So Spark packages, part of repositories that gets passed in here is, so that's all hidden. If you do an export, although don't do it now because you guys are tailing, but if you export, you'll see Spark repositories is going to have a whole ton of crap in it. Spark submit jars. This is just more about just being aware of the environment here if you do go to reuse this. So here it is. Here's this 1.5 class Maven repo, Spark-packages, Maven, and then here's the rest of the world here. Spark submit jars. This is, let's see. Yeah, this is just kind of one-off jars. Like you'll see the Spark Core NLP stuff in here again. Like I said, like setting up Core NLP with the Spark ML pipelines required a lot of work, and I've created issues, and I don't really get anywhere with it, so I just keep the hacks in there. Spark submit packages. This is cool. Spark submit packages. Not sure if you guys knew about this, but you can specify Maven coordinates. That's the jars. So these are Maven coordinates. Just take one for example. My buddy Tim Hunter, tensor frames. This usually goes where it's the order. It's at the beginning if I've added it recently, just because I'm too lazy to scroll down. So this is tensor frames. So this is an actual repo, GitHub repo. This is a Maven jar. Here's the max mine geo translation. Here's the Dynamo Netflix stuff. So these are all, just to get everyone on the same page, within search.maven.org. TJ Hunter. How did that, Netflix Dyno, there's all the Dyno stuff. Yeah, the Netflix Dynamite. Yeah, I'm not sure. I think I forgot to mention this. Someone asked about Dynamo. Did I tell everyone about the Dynamo? Yeah, this package from Netflix Dyno, Dynamite, which I was talking about earlier today, the term comes from the Dynamo paper, which is also where DynamoDB gets their name, from the Dynamo paper. It came out of Amazon. It's a pretty famous paper, I don't know, 2008 or 7 or something, but yeah, very, very famous paper on how to tune consistency and availability, and it's basically what DynamoDB is. And so, yeah, Netflix created it, but let you plug in Redis and Memcache, that kind of thing. Anyway, so let's keep on going. I'm passing in all these pretty much on every Spark submit, just in case I miss a dependency. So here we go, specifying the class, Spark Pi. Master is going to be the same that you guys pointed to. Me. Number of executors. Let's see. Number of executors. How do we want? So that's physically number of JVMs to seek out or allocate. So this is on a per job basis. Let's kind of skip that one for now. But the executor memory. So this is important. This is the one value that's really, really temperamental. And this is the reason I kill all of your shit before you run this, is because if there's anyone in this cluster, and I don't remember Spark ever doing this, so I don't know if I have something misconfigured or this, but if there's any worker, if I specify 48 gigs, I want 48 gigs of all of each of the executors, which is a JVM. If I specify 48, I thought Spark was a little bit more lenient on this, but maybe I just never pushed it. If there's any worker in here that's less than 48, the job just doesn't run. I don't usually request 48 gig. Usually it's 8 or 16 or something like that, so maybe I just never did it. Executor cores, this value doesn't really matter. It's just going to kind of, as long as it's high enough, it's going to gobble up everything we have. How many cores did I say we had? We had all right, so let's do like 500. Example, okay, so this is the jar that has this class in it. This one's interesting. This is number of partitions. Do you guys know how Spark Pi works? Yeah, how you would estimate pi in like a Monte Carlo simulation kind of way? Well, I'm here to tell you. It's brute force, essentially. So you know, if you're given a circle, so we're calculating pi, that's the use case. You can impress your friends and family today when you go home. If you know, so you know that this is a circle, you know you've got that dimension is the same as that dimension, the full thing is a square. If you start throwing darts at this thing, you can calculate the number of darts that end up over here, the number of darts that end up in here, and you can back into pi. Area of the circle, pi is pi is area of circle. Anyway, there's a way, when you figure out that ratio of the ones that are inside the circle and outside the circle, and you can calculate pi. So it's just throwing darts. So that's why this is like a fun one to do in a distributed manner. Because, is there like a video or something here? Because you can sort of, like brute force, do this in parallel and then kind of collect all the results back and then calculate pi, right? So the finer grained you are, the more partitions that you have, the longer that you let this run, the more memory you give it, the more accurate this is going to be. So we're going to get a pretty darn accurate estimation of pi. Okay, so when I run this, you guys just kind of raise your hand a little bit when you... Oh, and so number of partitions, this is pretty important. In terms of Spark tuning, you want to choose this value based on the number of cores that you have, usually between ×3 or ×5. Yes, I always go ×5. I just like to push the limits there. So if we have, what was our number? Do we have 230, 240, 240?
248 actually. Refresh this pretty much. Oh, 34, there's more. I need to.
Where is it coming from? What's taking you so long? Wow, look at the 1.6 terabytes. That's pretty sweet. So 272 times 5, 1,300. So I'm going to say 1,400, because I like to go on the high side. The thinking here is that you want to keep the CPUs hot, right? So you want to. This is actually one of the biggest performance gaining, just kind of quick, like low-hanging fruits. We would tell customers this, and they were like blown away. And it's like hidden in one little section of the Spark, tuning guide. Hey, by the way, multiply your number of cores times 3, between 3 and 5. It's changed with tungsten. It actually got a little bit better, so you can go higher. Before it was like 2 to 4 or something. Now it's 3 to 5. Anyway, I just put that. So 1,400. All right, let's do this. Yeah, so the thinking there is that you want to saturate the CPUs, right? So you want to over-provision 5 times so that stuff is just constantly sitting on the CPU and not waiting around. All right, I'm going to run this. Let's do it. Fingers crossed. DJ Hunter coming up there, even though it's not in the repo. You guys seeing stuff? Yeah?
Yep.
Let's see. Yeah.
So this 1400 multiplied number of cores by 1, but that was for the partitions or?
That's for a number of partitions, yeah.
But then consider non-spark pi programs. So what's that?
No, I mean, it's for like anything that could be distributed.
So
Any
it's
kind of algorithm.
only for number of partitions that you're expecting for RP.
You can, yeah, I mean, you can choose the number of partitions. Oh, yeah, I think I see what you're saying, which is, yeah, I mean, this is more for like just pure processing and not necessarily how the data is going to end up. Yeah, so this is different partition, right, than like data partition. Okay. It's just pure CPU partitions. It's like literally how many tasks do you want to break it into?
As one example, some of my jobs where I kind of partition to distribute out like this, my input is simply a list of files on HDFS. And I split it up onto one line per task, and then each worker will pick up that HDFS file, process it independently, and that'll be like a 30-minute job, but I can spin up 500 of them going at once.
Yeah, and in fact, I kind of glossed over the executor number. So yes, each of these executors is one JVM, and each JVM will then multi-thread within it, right? So like depending on the number of cores, right? So there's some kind of back and forth as to how many of the executors do you use. If you have like big machines, do you choose larger, that have 60 gigs of RAM and things like that. So some of the capacity planning stuff within Spark is still kind of a black magic. There's tons and tons of blog posts, about how to tune things, especially with Yarn. Yeah, Yarn's a tricky one to kind of get right if you don't know about a couple parameters. But yeah, I mean, at least think of like multi-threading within a single JVM, but then also multiple JVMs working in parallel on the same data set. Yeah, just ignore that. That's like the driver is telling you to calm the fuck down, kind of thing. Which is probably nicer than.
Do you have speculative execution turned on, or?
I don't usually. I don't remember. What's the default? Because I think I don't remember.
Anyway, that can be a cause of killing. Is it'll sometimes send the same thing to 2 workers to see who finishes first, and as soon as one gets finished, it's like, oh, that job's done. You can stop what you were doing. If there's not enough work to go around, it'll have 2 people doing the same task in case one fails.
Yeah, SpecX, yeah, where it's kind of, it's like trying to pin stragglers and things like that. We typically would advise people not to turn it on. But
right. And there's reasons to do it, there's reasons not. I don't know what the setting is.
Yeah, I can't remember what it is by default, but. So here we go. Pi is roughly 3.14149. Man, we're so close. So yeah, check out those ASCII graphics right there, huh? I still can't figure out how to read this. I've asked so many people, no one can explain it to me. Okay, so we did Spark Pi, that's badass. We believe in ourselves, our cluster is stable. Let me see, we actually lost a worker. No, okay. Saw one dead worker. Okay. Anyway, let's do another one a bit more complex. So do you remember the matrix factorization? We never actually got to look at the notebook, but it was, which is why I think that dude left, because that's all I wanted to see, was the damn notebooks from this morning. So this thing. So we're going to do this, except not on our small data. which was the collaboration here. But we're actually going to run it on the movie lens dataset. So it's basically running this exact code, except with a larger dataset. So this is ALS, the alternating least squares. Very, very parallelizable, right, like algorithm, which is why Spark loves it. Yes, anything that can be broken up into chunks and then sort of collected later is perfect, is super right for a Spark cluster. So let's do the same thing here real quick. I don't know if this takes number of partitions. But yeah, that's what's cool about the Spark Pi is that you can specify that. Oh, one thing about partitions too, and again, this is like a tuning thing. This was brought up, I think, the other day at the meetup as well, but there's this Spark, let me find it. Is it Spark SQL shuffle partitions? This is the single most potentially crippling parameter if you don't know about it. I'm just double checking it's still here in 2.0 because I thought they were getting rid of it. Parallelism. Is it really not in 2.0? That would be wicked. Okay, do you guys remember the name of that? Is it shuffle partitions? Anyway, the default is 200. So if you're running a Spark SQL thing, which is 99% of what everyone does with Spark, if you're joining tables and things like that, if you don't specify this configuration parameter, by default, it's just going to choose 200 partitions. Is it, what's the name of it?
It's under the
Okay. It's still in Spark 2.0. Yeah, here it is. This is your worst nightmare right here. This guy. What sucks about this is that, right, yeah, I mean, pretty much all of the Spark, like the Spark API, Spark, right, yeah, the machine learning stuff, all pretty much uses like data frame speed recovers. So all queries or all jobs that you're running, even though you don't realize it, Spark SQL is behind the scenes. And so this is number of partitions when shuffling. So it's number of reducers, right? Your number to use when shuffling data. So if you have this number set to 200 and but you know that you want to like split it up even more, right? Because what happens quite a bit is with large data sets, if you only give it 200 partitions, each partition has a huge amount of data and you'll start seeing out of memories. Like you're not supposed to see out of memories anymore after Spark 1.5 or 1.6, but you still do. And the super quick low-hanging fruit is to just add another 0 onto this thing and just see what happens. This is like the number one thing people would come to the booth at Databricks conferences. They would come to the booth. They had a huge stack trace, and there's like 100 people trying to talk to us, and I'd be like, yeah, just bump up that one value. He would go away, come back. He's like, got it. All right. Like, yeah, this is all it takes. This one, and then this is the auto broadcast join threshold. Is this still in 2.0? Yeah, this is that 10 megabyte thing that I was talking about earlier, where if you look on disk and you see your small table is 10 megs, but when it gets loaded in, it's actually a lot more than that. Actually, come to think of it, with Project Tungsten, and I haven't verified this, but this might not be as skewed as I described it, right? Because when you're loading in data now with Project Tungsten, it's pretty close to the actual size on disk because there's not a lot of overhead. But yeah, this was definitely a problem for a long time. So keep an eye on these. Anything Spark SQL is pretty much always used beneath the covers for anything Spark. All right, so let's do.
But you'll go back as we go back later.
cores. Here's 500. Okay. Same thing.
All right. Well,
Master ID, change master ID.
Or wind beneath my wings, people.
yeah. All right.
All right. I'm not looking. A little hand wave. You see stuff happening. Stuff's happening. I should have like an award, like a prize for the first person, because it's pretty much random. You guys seeing stuff? Yeah.
Yep.
Cool. So let's poke into this thing while it's running. So this is generating recommendations. So remember when I said that every job that you run has will listen on its own port for admin purposes. That's where I'm at, port 4040, because I killed everything else. And let's see. So this is a very iterative algorithm, right? It's like it's breaking things up, going back and forth, back and forth, back and forth, and collecting everything. One thing you'll see is this skipped stages. I was explaining this to someone earlier, I think. This is a secret, hidden, like optimization that nobody understands really well. I have a hard time explaining it. Is that finished right? Oh, finished with the stack trace. What? Oh, yeah, no, here we go. So these are the recommendations for, I can't remember how I had this coded, but yeah. So that was lickety split. Yeah, I don't know what that error at the end was, but skip stages. This is a secret hidden optimization. So, picture a stage, there's stuff being shuffled from one stage to another stage. It's going between nodes, between physical servers. If on the receiving, or no, on the sending side, the stage realizes that the receiver has already received that data. So when data is about to be transferred across, it's being stored locally on the mapper, and then the receiver comes in and pulls it down. If Spark can determine that nothing has changed, this is an iterative algorithm, so it's like iterating, working on parts of that matrix, nothing has changed here. That data hasn't changed, it's just going to skip that shuffle. And because it knows that the other side already has it. Or thinks it, and then when both sides say, yeah, like I have it, that's cool, then it just skips that stage. You can actually take advantage of that quite a bit, right? It's not deterministic, it's not guaranteed, unless you really have control over the environments. And it's not a multi-tenant environment, or multi-tenant where there's a lot of different people submitting jobs. So one thing actually, I was telling someone else this about Netflix, is every job, big job that they have, like serious job, like doing something like this, right? Yeah, it's like generating recommendations for like 120 million people or whatever. They run it in their own cluster. So they reserve enough EC2 instances where on a per job basis, they know that they're the only job. So they submit the job through this tooling that they have, and they can say which version of Spark they want, which version of Presto, whatever they want. basically, like behind the scenes, cobbles together this environment and then submits the job. So what's cool about that, and this is where I think Netflix, you kind of have to trust them, it's way easier to like debug something when you know that you're the only person on that server, right? So if you're trying to figure out what's wrong with my job, why is it so slow, why is it this, why is it that, why is it using this much memory, it's way easier to sort of keep it isolated. Like not all of us have Netflix cache, so it's a little tough to rationalize just spinning up and, but if you're going to reserve enough instances and throughout the day you're not using them as much as you are at night because you're streaming at night, things like that, you can do these kind of tricks. So, yeah, I mean, if you can start with that and have everyone launch jobs on their own cluster, that's the way to go. Very, very easy to reason through. And then the other benefit is this, the skip stages. If you're the only person on that server running these same jobs, you know that that local disk, it's physically the local disk on each of those nodes, but there's only so much of that disk. So once, if that gets cleared, or think of like a cache, like an LRU cache, if there's other people on there bouncing stuff in and out, then that stuff's going to get evicted, and then you can't skip stages anymore. So huge, huge savings. I mean, I think you saw on there, there's like 200 skip stages, and there are only 1,600 stages or whatever total. So. Right, does that make sense? There's been, for my meetup, I think 2 or 3 months ago, we had one of the Spark committers come in and talk about specifically that. There was like a whole 45-minute segment on just skip stages. Because A, no one could explain them, and B, it's a huge caching thing. Spark community has been like a little hesitant to expose that and to really have people rely on it, because of course it could go away at any point, and blah, blah, blah. If you know what you're doing, that's big savings. I think I have one more here. I don't know if I've actually ever gotten this one to run, or I haven't tried hard enough, but this is the similarity pathway, the couples compromise recommendations, but on a larger data set. Oh yeah, and then you want to see TensorFlow? That's Andy should show my demo. Yes, Andy and I paired up this week and sitting at a bar checking this out. Andy has a better version. Right, like, did you pretty it up too? Did you make the UI look nicer? Because the UI is shit. I'm going to show an example, TensorFlow.
What is TensorFlow?
Yeah. Oh, good question. TensorFlow is Google's neural network. I guess you could call it like more of a map processing or like library. The full runtime is based on C++, written in C++. There's Python bindings for it to make it more accessible to like normal people and data scientists. Let me show you what it can do. So I've got some examples here. We're going to call into TensorFlow itself. Given an image, here's the image. I was at like Zillow the other day, so I chose this. These are what TensorFlow has been, so like this particular model, this is the Google, it's called the ImageNet like data set that they've been training for years and years or whatever on all the images that they have and all the like contextual information. So based on that training, which is all supervised training, right? Like neural networks currently have some drawbacks when it comes to unsupervised, but these types of, so it's like scrolling across using convolutional neural net, boom, boom, scrolling, trying to figure out what this is, and then it comes up with these categories. So it's pretty sure, right, so like relatively, this is kind of a relative score, it's like pretty sure that microwave is in here. dishwasher. So what was cool about this for the Zillow folks is that, this is how you can find similar pictures without a human going in and tagging. This has been tagged offline with millions and millions of pictures, and now you can actually do it. There's this company, Clarify, C-L-A-R, starting to lose my voice, Clarif.ai. This company is pretty cool. So I think their current bread and butter, there's like two things that they have that's cool. There's this like iPhone app where it goes through all of your pictures, which I describe that to people and they're like, fuck no, you're not going through my pictures. Yes, I like it because it like categorizes different pictures, and it's more than just the Apple Photos thing where it's like, here you're in San Francisco, here you're in Seattle kind of thing. So that's kind of the fun consumer thing. And then their sort of business-to-business thing is like detecting porn. Which for me, anyway, I was gonna say, I like to detect porn, but these businesses don't like porn. So, especially user-generated content, right? So you're a site, you don't want this huge fleet of like Mechanical Turk people or something going through and trying to figure out what's porn and what's not porn. So based on like the different ratios and skin tones and things like that, you can figure out. So yeah, the adult content, that's kind of one of their that's one of their big money makers. But yeah, try out their, I guess it's called For Every now. It was called something else before that. So let me show you guys TensorFlow. And you can do this on your own. I don't know if, you probably have to maybe start up Spark, I'm not sure. This doesn't depend on Spark, but the way that I've got the notebook configured, it's depending on Spark too much.
And now, did the similarities succeed? Because I got bugged also.
Yeah, wow. The base path. Oh, you know what, this is the small data set. Oops. So I must have changed that recently. Yeah, that was only like split seconds. So here's some fun things you can do with TensorFlow. Yes, I went to this GPU conference, the Nvidia GPU Conference, GTC, GPU Tech Conference, a few months ago in San Jose. It was probably one of the best experiences I've ever had. Like, I thought it was going to be just like a video game convention and like Comic-Con, but with circuits and chips and things like that. They actually have a big data track, which is cool, and it was all ML and it was all neural nets. And this was actually one of their demos. And you can do fun things here, like there's this project Deep Dream that you can kind of morph and take like one image and then morph it into another and just like have it stop at certain features that it picks up. There's a lot of this thing that show you fun stuff. So here's a picture, it's trying to classify it. Figures out parachute, out balloon. And then you can have it render and sort of like mix in. Yeah, I mean, these are the classic ones, I'm not going to spend too much time, these are pretty Googleable. But because this, like ImageNet, like data set has been trained with so many dogs and cats and things like that, these things tend to show up pretty prominently. Oh, yeah, here's the cake. Picture of me after a bad Saturday night. Oh, here's my pancake bot. Yes, I haven't talked about that in terms of the pancake stack. This 3D pancake printer. Takes 45 minutes per pancake. I had huge dreams for that thing, and it's just been such a letdown. One thing about, so TensorFlow, just to show you guys kind of a quick, TensorFlow Fundamentals. This is what we used a couple months ago. Me and my buddy Sam, soon to be my roommate, he's actually moving up from LA to San Francisco. We did this Spark plus TensorFlow workshop. So this is one of the more fuller featured notebooks in here, is under the TensorFlow Fundamentals. So it kind of gives you an idea. It's this kind of wonky like programming environment, or like programming. So yeah, this is all Python here, but like the way that you're setting up placeholders or variables and giving them names like this, and then you kind of build up like a DAG, you know, similar to Spark, of these operations, and then when you submit it, you know, you first have to create a session, I think probably. There's a session created somewhere. You sort of have to manage your own sessions, and yeah, here it is. So here I've like built up a DAG. I'm telling you what to do. I'm saying add both A and B, then multiply A and B, and add C and D. And this is some of the output logging. So yeah, here you build up the session, then you populate the variables with values into the DAG. And then you run the session. Yeah, so Google has been kind of clever in saying that like this isn't just a neural network library. This is like a linear algebra library. This is like a mathematics library, right? It's got a lot of you know, like neural net concepts built into it. There's a higher level library that you can write to that's on top of this called Keras, or Keras. Which looks like it's broken right now, but you can actually, you know, sort of speak like a neural net language, right? So you can actually speak to this. You can say, this is the activation, like algorithm that I want. This is, yeah, like the number of nodes, the number of neurons, the number of layers, and then it fills in all that session management and all that sort of low-level TensorFlow stuff. So there's a lot of support. Yeah, I've always been hesitant of sort of Uber frameworks that let you plug in, but with Keras, you can plug in TensorFlow, you can plug in Caffe. I don't know about the other, but and then it'll generate all the code kind of beneath the covers, or plugins will do it. So that's something to keep an eye on. Let me show you guys one other thing that's really slick. Playground.tensorflow.org. So this is going to blow your minds. This wasn't a Google project, but Google picked it up and put it off the main TensorFlow site, where you can actually choose. So here we're trying to classify. It's kind of the starting point to the upper right. So here the problem type is classification. These are some of the activation. What's really sort of interesting about these neural nets is the math is like surprisingly simple, right? And so actually, if you guys keep an eye on my meetup, at the Advanced Spark TensorFlow meetup, next week we're actually going to have Sam is flying up. He's going to drop off some shit at my place, and then we're putting him right to work. He's going to talk about these activation functions and sort of the primitive concepts behind the math of neural networks. Because there's really only a few concepts that you need to know. The whole back propagation, and what does that mean? Like, how do you know which neuron to back propagate to? Pretty much the most complex math is partial derivatives, which I'm sure we've all done at some point, some of us 20 years ago. So here I'm choosing classification, and I'm going to pick these crazy data sets. Like, how is it possibly going to classify? Well, actually, let's pick this one first. So the goal is to sort of find some set of weights, right, that create this formula that can separate these two data sets. Right, so let's put this to work. So learning rate, yeah, you can adjust some of these things. We'll just press play here. So you see slowly, so this is the error. So very quickly it figured this out. I can pause it. So this is the training, yeah, so this is the actual like loss function here. So it goes straight down, like figures it out pretty quickly. This is what we do. You can see, so these are the two input nodes. There's for this particular case, there's 2 nodes, there's only 2 axes. So it's either is, blue on this side is the tan on like that side kind of thing, and then the other one can only do up and down. And it's slowly feeding this information in. This is telling you over here, no, that's not right, this is what it looks like, make these changes, and it back propagates. And the key is the back propagation to know specifically which of these neurons to update. So what you're doing is, yes, there's gradient descent. Yes, that's being deployed here. And it's figuring out which direction should I go. Right? The gradient descent is you take derivative and figure out, like, am I going down or am I going up? Yeah, which way is the best way to minimize this error between what I'm guessing from this network to what's actually true. So again, this is supervised. And it's back propagating, it's making small little changes here. The thickness of these tells you how much influence you have on the node in front of you. And it's sort of, it's starting off guessing, right? So it's just kind of picking, and then like those guesses turn into like going down, going up, or like making these small adjustments to the weight. So it's pretty much a brute force technique. But it's, yeah, and so you would like add layers and test the performance, right? So if you're going to add layers, that's going to typically add to the training time, add to the scoring time as well, the actual prediction time. So when this neural network is done being trained, when you actually go to predict, you're just doing a forward propagation. You're just starting with these inputs, just putting in your weights, and boom, that's the answer coming out. But during training, it's doing forward and back, forward and back, forward and back. So, yes, I say keep an eye on the meetup because we're going to tape it. Who the fuck says that? And then post it to utape.com. It's getting late in the day. So let's pick another completely ridiculous data set. So it needs to get in here and crawl around and figure out what's going on. So these guys are going crazy. It's like, I don't know, dude, this is all I have. These are the only like axes that I have to work with. I can either tell you it's on this side or this side. Yeah. So that took a while. And then this one should be pretty quick. Yeah, I want to go straight to it because it's just like that. So that's kind of the intuition behind these neural nets. If you think of things like image classification, this is using convolutional neural networks. The term convolution, think of not just looking at like an image pixel by pixel, which is what we did before when we were doing similarities. We flattened out those 50 by 50s into 2500 and then compared the grayscale values. With convolutions, you're sort of expanding beyond just the pixel, and you're maybe going 3 by 3, which is pretty much the most common. Scrolling along, scrolling this way, figuring out where the edges are, right? So this is why these neural networks can actually detect similar faces, right? Even if they're skewed slightly or turn this way, that kind of thing. You can adjust for those different angles. And then the other one, so if you think of images, think of convolutional. If you think of natural language processing, this is going to be the recurrent neural networks. So there's CNNs and there's RNNs. With RNNs, really good blog post here. But the intuition here is what you're trying to do is, so for example, predicting what sentence will come after. So I think off the Tensorflow website, there's a pretty fun demo where you can actually, there's this data set that's been trained on the Obama speeches. And if you type in a sentence, it will make suggestions about what it thinks the next sentence will be. It's some Obama, ridiculous phrase or whatever. Did you guys catch that Obama used the word jibe a couple weeks ago? Did anyone think that was weird? He said, "This doesn't jibe with the American people." It was in CNN, closed captioning jibe. So if you're trying to predict the next word, or speech recognition, things like that, what you need to do is store a tiny bit of state. With convolutions, you just kind of scroll around and kind of do your thing. If you want to use current data to predict the next couple chunks of data or the next couple sets of words, you have to store a little bit of state. And you have to figure out, so picture GPUs are very, very limited RAM. At best you might have 12 gig or 16 gig or something like that. So these GPUs can't really hold on to state. And if you're dealing with a lot of text, there's a lot of state. So you have to sort of, in a probabilistic way, figure out what to toss out and when to toss out. And then replace it with something more valuable. Yes, Andy, do you have anything to show on the syntax net stuff? Probably not. Yeah, he and I tried to tackle syntax net at like 10 p.m. at a bar that was closing. There was just all kinds of sadness. So if you picture one example, you're sort of scrolling through text and you hit a pronoun that's a different gender. Right? So all of a sudden you hit he. So now you can toss out any like feminine or plural words, right? So he, we're now, the next couple words will probably be something singular and male in general, something like that. So with fairly high probability, you could throw away anything that was both plural and female. So yeah, that's kind of the high level thinking there. Yeah, I mean, I'd encourage you guys just to kind of look at the math behind it. It's pretty interesting. There's gradient descent, there's, the partial derivatives, and yes, all of these frameworks like TensorFlow and Theano give you the auto differentiation. Like they basically calculate the partial derivatives for you. Yes, previously this was difficult stuff. This was done by hand. It wasn't very straightforward to do. But yeah, next week Sam is going to break it down, and we're actually going to calculate a partial derivative so we understand, we can remember how difficult it was, and then appreciate why these libraries exist. And how they can target specific neurons. One last thing about TensorFlow, and it's 5 o'clock, I want to point out the history of neural networks has always been in this cloud of how do we reason through this prediction. So with machine learning, this is fairly decent. Certain algorithms, you can point people and show them linear regression, show them logistic regression, can give some hints. If you're talking to management, you're talking to a friend, or trying to explain how we got this prediction, you can kind of reason through it. These neural networks, it's pretty much like these activation functions, gradients, trying to figure out which way to go up and down, and how does it learn. And, it's always been difficult to reason through how we get to a prediction. So this is something that Google has been very sensitive about, so they've chosen to treat this as a first-class citizen. So there's this tool called TensorBoard, that's a first-class citizen within TensorFlow itself. It's been there since the beginning. And if you guys, I think I kind of zipped over it, but you could see at certain points within training, this TensorFlow Fundamentals, where we're actually writing out summaries. So we'll see this TF scalar summary. It's a summary writer. And summary writer is responsible for sort of collecting things that you tell it. So you have more control now during training about where did we get the decision to go up or to go down, or things like that. So, and this is all being written in a format that it just starts up as a web service, basically, this UI. And it's going to end up looking something like this. So you can kind of scroll through and see how quickly did we minimize the error. We can see the events that fed into it, which are the events that we have control over writing out to. So again, this gives more sort of insight into how we got to the model that we got to. One thing I did, we had a session, workshop actually, I think it was 2 months ago now. I still have to post it to the meetup site and everything, and to like YouTube. Off of Pipeline.io is all the YouTube stuff. So everything down here, this is the YouTube, here's all the slideshow. These are all clickable links, people didn't realize that. I guess I wouldn't either. But yeah, if you keep an eye on this YouTube, it's actually, I've got it all uploaded to YouTube, I just have to build the descriptions. It's a full, yeah, I did my spiel, like this whole 8-hour thing in 4 hours, and then I had 2 TensorFlow guys come in and speak for the second half of the day. And they covered end-to-end this Tensor Fundamentals, distributed TensorFlow, that's one of TensorFlow's big selling points, is that it can run in a clustered manner and choose GPUs, choose CPUs, can figure out which operations in this DAG that we built up, which ones are best suited for the GPUs. So yeah, check that out. It's about 4 hours of TensorFlow. Skip the first part because you've already heard me talk for a full 8 hours, but the second half is pretty good. So that should be up hopefully by tomorrow. Actually, I just need a good like hour to sit down and make it all pretty. But yeah, that's it. Oh, the cloud instances, yeah. I tell people I'm gonna tear them down at midnight, and then I get drunk, and I don't think about it until like 10 a.m. the next morning. So I don't know if I'm gonna get drunk tonight, but yeah, probably tomorrow morning. It's always there, yeah. And it's the same exact Docker image. It was burned last night, the same one I'm using, the same one you guys used. Yep. If you, yeah, multiple people have been asking about getting it to run locally. This is a big ask, I know. Right now, at a bare minimum, make sure that you use the new Docker for Mac or for Windows. Looks like I'm still on the beta channel, but they do have a release version. And try it. I mean, I think you need at least 16 gigs. If you do any of the TensorFlow stuff, it's going to probably not be enough. Some of that training is about 24 gigs. But all of the TensorFlow code is in those notebooks. And then off the wiki, there's this TensorFlow support. Yeah, I don't know why it's called support, just what I came up with the other day, but this is like everything. Yeah, so this is really most of the training side of what I was able to really do with that classification demo. But the training of that takes about 24 gigs. So yeah, that's the only thing. You know, yeah, follow these steps as best you can. Maybe try to work around it. But yeah, that's it. That's what I've been doing the last couple years of my life. So thanks for sticking around. One thing, so this whole batching up of like dot products, it's one thing to point out too about matrix multiplication. I don't know if I'll be able to find it here. I switched laptops a couple weeks ago, my laptop was still on. One cool thing to keep in mind, this is sort of the bridge of like systems and application design and things like that. So this is from one of my old talks. This is actually out on SlideShare already, but if you're doing, I was thinking about this on the way over here this morning, that I want to make sure I got this in, so give me a sec. But if you're doing, one thing to keep in mind, thinking about systems and matrix multiplication, if there's, this is a huge, cache friendly, cache 90. Okay, so if you're doing dot products, right, probably remember you would go this way for the top and this way down the bottom for the column. So in the actual CPUs, right, like the actual registers, so what you're trying to do here is basically let the CPUs do like proper prefetching, right? And if you're going this way across the top, this is very friendly from a memory standpoint. If you're going down the bottom like this, you're skipping, right? So if the data is stored in memory, you actually prefetch the 1 and 2 by B, and then just grab the 1 and then throw away the 2. And then grab 3 and 4. Right? The pictures is a much larger matrix. So if you're trying to do this, you can actually, this code is part of, this is some of my earlier code, but you can actually run this code. It's in Spark Core, or it's like MyApps Core or something like that. And then if you just do one simple thing where you transpose B, now you can traverse like going the same way for each. This is a huge performance speed up. It's like crazy. I think I have the numbers. I think it's even different than this too. I think this was, but yeah, I mean like a 10 times increase just by flipping that one matrix. Now of course, actually in terms of cache prefetch misses, this is the overall time was 10, but yeah, look at this, 72 times the amount if you do it the naive way than if you like transpose it. Right? So of course, if you do a transpose, that's going to occupy cycles, but probably might be worth it if you do have these huge matrices to do it this way. And also too, just like Parquet on disk, right, so if you guys know much about Parquet, it's storing everything in a columnar way, so it's storing, right, because these are like typically these analytics workloads where you're summing things and you want all of the columns, or the values of the columns to be next to each other on disk. It's not just good from like a data locality where I can get the, so say that we're trying to average, like find an average age. So you would rip through, please take a pizza too. You're going to rip through all of the ages right next to each other physically on disk. So that benefit helps you also, not just on disk, but also in RAM. Because it's not just the fact that all those ages are right next to each other physically. You would seek once on disk and then zip across, like grab all the ages and sum. But you're actually, in memory, you're also prefetching, both on disk, if you're doing it on disk, and then also in memory. You're grabbing so you're never just grabbing the next item that you want. Like you're always grabbing the block size or something. So even in RAM, storing something in a columnar format. And so this is actually, the closest project out right now is the Arrow project. It's the Apache Arrow, and the first tangible component of it is Feather, and it's a way to get data in between R and Python and Java and things like that in a columnar, in a standard columnar format. So this is such an important concept that just standard. Yeah. Exactly. I know. Yeah, that's true. Yes, are they Apache projects? I just saw it talk about Wes on there, so it's like columnar. Yeah, so don't think of columnar as being good just for the data locality, but also it's also very powerful in memory. Right? So this was all in memory. I just flipped it, and the prefetch misses went way down when I translated. Thanks for staying. Was this useful? Yeah, this is always fun to ask the people that stick around, because it's usually a yes. I should be asking.